So I had a quick look at this question and I've already solved it as usual. And overall, it's actually quite straightforward. There's nothing new about this question. It's just typical resolving forces, perpendicular ones, a typical two-pulley system. If you've done the previous M1 papers, then this will come to no surprise. It's actually a lot easier than those even. And there is no complicated question as in how far does A travel or when does it hit the pulley, etc. You get nothing like that. This is very simple final question. But anyway, let's have a look and try and walk through all of this. Yeah, I'm going to go ahead and label this diagram as I'm reading the text, and we'll compare it to the final diagram and use it to solve the rest of the problems. So let's do this. So let's begin. A small ball A of mass 2.5 kg is held at rest on a rough horizontal table. So here's the mass A, and with these kind of diagrams, always draw forces. So here I'm going to draw a downward force because it's held at rest, and that's representing the weight of 2.5 times the gravitational value of 9.8. So that's done. And of course, just looking at B, we can put 1.5 G here as well. Easy stuff. Now the ball is attached to one end of a string. Okay, so since this is a string, we have to assume that there is some form of tension coming off it over here, and of course tension here. Oh yeah, by the way, because this table is rough, there is also a force going back that's on the ground. So this is the rough ground. Okay, so there is going to be some friction. Now we don't know if there's a value yet, so we're going to keep reading. Now the string passes through a pulley P over here, which is fixed at the edge of the table. The other end of the string is attached to a small ball B of mass 1.5 kg hanging freely. Okay, and it's vertically below P, with a height of 1 meters above the ground. Now the system is released from rest. So if it's released from rest, there's a good chance that this ball is going to slowly go down, dragging this one with you. Okay, with the string taut. So taut means it's tight, so the string isn't slack at all. The resistance to the motion of A from the rough table is modeled as having a constant magnitude of 12.7 newtons. So that's the resistance, that's the friction. So we don't even use the mu coefficient here. We actually have the full force. This, like I said, is easy. Okay, and yeah, because we know it's moving due to acceleration, and the B is going to fall down, we're going to put some acceleration factors here going downward, because we know A travels horizontally and B is falling down, so it's going downwards. Okay, so always label it down as much as you can. Okay, let's keep going. Right, so the balls are modeled as, okay, ball B reaches the floor before ball A reaches the pulley, so that's cool. So we can say that the distance from A to P is greater than 1 meters. Now the balls are modeled as particles, and the string is modeled as being light and inextensible. The pulley is modeled as being small and smooth, and the acceleration due to gravity G is modeled as being 9.8. Standard stuff, very standard. Now A, write down an equation for motion of A and for B, and B, hence find acceleration of B. Okay, so I'm going to do parts A and B together. Now the first thing I want to look at is firstly, how do we model equations? Well, we always model in the direction of the force, so going right. So we always model the direction going right at A, and we follow the acceleration at B, so we resolve going downwards for particle B. Now I'll show you what I did here. So this is the same thing. Got the tension T, so I don't know if I even labeled this tension. Yep, I did. Now resolving at part A, so we're resolving to the right. We can see that if we're resolving to the right, that means the tension is positive and the value behind is negative, so T minus 12.7, and it always equals MA, mass times acceleration. So it's always the resultant force equals mass times acceleration. So mass is 2.5, acceleration is A. Now I'll do the same for the downward force. So resolving downwards, i.e. following the acceleration, we have the resultant force of 1.5 G, which is positive now because it's going downwards, and upwards is negative, minus T. And it's equal to MA, 1.5A. Voila. So this is your equations of A and B. Now, we have to try and solve this to find the value of the acceleration. We don't care about the tension, which is alright, I guess. And to find this, it's just simple simultaneous equations. What I did is that I decided to just add both equations together. Because if you add them, the T values cancel out, because T minus T is 0. And then you're left with 1.5G plus minus 12.7. So I left it over here. And then 2.5A plus 1.5A is 4A, and then divide by 4, and you have your acceleration. So that's literally part A and B done. So easy. Now let's look at C. So like I said, guys, this is a very simple question. Now using the model, find the time it takes from release for B to reach the floor. So we know that it's 1 meter away at the moment. So what I did, I resketched this diagram as over here, and I'll explain it. So here's the particle B right now. So we know it's a distance 1 meter from the floor. So we can firstly say that the distance S is 1. We know that it's released from rest. Now this is very important. If it's released from rest, it means that the initial speed U is 0. So here we go. We know that the acceleration is constant and it's going to go down at an accelerating, it's going to accelerate at 0.5 meters per second squared. So that's at A. We don't necessarily need to know the final speed as it touches the ground. We just care about the time t. So firstly, so what you should always do is write a set of SUVA equations. Yeah, so write SUVA and fill out your variables. S is 1, U is 0, V we don't need, cross it out. A is 0.5 and we're trying to find t. So we have 1 unknown and 4 terms, which is perfect. Now finding a suitable SUVA equation, pick one that doesn't have V in the formula sheet, and you should come to this one. S equals UT plus half AT squared. And just pop in all your values. So S is 1, U is 0, so that cancels out. And then half AT, half times 0.5 times T squared. And then tidying all this up, you get quarter T squared, or T squared over 4 equals 1. Timesing 4 across and square rooting. And your final time it takes for the ball to hit the ground is 2 seconds. Done. Easy. Yeah, so we're almost done. Now, let's look at the final bit, D. Okay? Now, D is very straightforward. I'm going to just leave it so you guys can see it. So, suggest 2 improvements that could be made in the model. Now, this is very just common sense. No, not common sense, but this is just depending on what you understand about the forces in general. Now, one thing I always use for these questions is the gravity value, G. G is fixed at 9.8, but to get a better result, a more accurate result, it's better to use a less simplified value. For example, like 9.81 or something that isn't too approximated. You want to pick you always want to improve the value of G by picking the one with the least number of rounded figures. So that's one. So I wrote here, what did I write? Use a better approximation to the G value instead of 9.8. Simple. And I also talked about the ball. Because we don't know much about the ball, we model it as a particle. And something as a particle has no weight. But if we give the ball actual dimensions, okay, it's a lie, there is a weight. If we give the ball actual dimensions, then it would actually change for example, the speed of the ball falling down. So something with actual dimensions will actually affect the ultimate run of the ball. So I wrote here, ball, add dimensions so falling distance can be calculated more accurately. There's other things you can discuss, for example, the surface itself being rough. We want to know the actual coefficient of friction here, and maybe it's rough at different places. Maybe the pulley as well, if it wasn't parallel or if it was in a different position, the ball distance will fall. There's quite a few things. And oh yeah, something they don't mention is air resistance. If there was air resistance, then that might affect the drop as well, and so forth. That adds another drag. It's like another type of friction again. So there's various types. I mean, they just want 2. So, and the easiest one is the value of G being better and the dimensions of the ball. Simple. But yeah, guys, if you enjoyed this video, please give me a like as always. And otherwise, I'll see you guys down the road, innit? Take care.